Hey everybody, welcome back to All the Math. That's all the math you need for computer science. This is episode 5 of volume 2. We're going to be talking about linear transformations in this episode. And it's basically another way of thinking about a matrix. So it's not really a new operation or a new object. It's a new way of thinking about one. So basically what we're going to do is take a matrix, which we've been thinking about as just a two-dimensional array of numbers, and think of it instead as a function. Okay, we're going to think of it as a mechanical operation that takes an input and gives an output. So you've already seen this when we look at matrix vector multiplication, right? Let's say we have a matrix here. I'll make it a 3 by 2. I'll just give it some entries there. Now, what we're going to ask is, first of all, if I wanted to multiply this thing by a vector over here, what dimensions would that vector have to have? And then the next question we're going to ask is, what are we going to get out of it when we do the multiplication? All right, so you remember the answers to that question. The answers to what dimensions does it have to have is, this thing has got to be a 2 by 1, right? This has to be 2 tall because this is 2 wide. And we need to make sure that that is the same distance as that, so I can multiply it by 3, 5, or something, right? In order for the multiplication to make sense. So if this thing isn't a two-dimensional vector, you can't even do the operation. All right, so that's the answer to the first question. What does the input have to look like? Because what we're going to be doing is treating this vector as an input. And when we do this dot product here, when we do this matrix vector multiplication, we're going to get something out. And the question is, what are we going to get out? And the answer is, we're going to get out a 3 by 1. Why is it going to be a 3 by 1? It's going to be a 3 by 1 because there are 3 rows here. And remember, we're going to take 2, 4 times 3, 5 and get a dot product that goes here. We can work that out. That's going to be 6 plus 9 is 15 if my math is right. And then we're going to take 1 negative 5 times 3, 5, and we're going to get back 3 plus negative 25, which is negative 22 if my math is right. And then we're going to take 9, 6, 3, 5. Oh man, big numbers. 9 times 3 is 27. 6 times 5 is 30. Okay, that's not so hard. 57 is what we get out here, right? But the point here is we're going to get back a 3-dimensional answer. So this matrix here, let's call it A. We could view A as a matrix, or we could view it as a function that is taking a vector in R2. Now, if you don't know what that means, that basically means two-dimensional real numbers. So that means ordered pairs of real numbers, like 3, 5 is our example here, or it could be any real number like 1.4, negative 2.59, right? So these don't have to be integers, but any number in R2 means any ordered pair of real numbers. That's what that means. And this function, that's its domain, and its codomain, which is what it maps things to, and by the way, this thing is called a linear transformation. It's also called a linear map, takes it to a point in R3. So you give me a two-dimensional vector, I pop out a three-dimensional vector. And that is called a linear transformation. And it's called linear because we are doing matrix vector multiplication, which can only produce a linear output, as we've talked about a little bit and as we'll see a little bit more here, right? And it's called transformation because we're transforming it. And in general, you can take an n-dimensional vector and you can produce an m-dimensional vector. N and m can be the same, and as it happens, that turns out to be the most interesting of all the different kinds of linear transformations, is when you're transforming R3 to R3 or R5 to R5. Now, when I first learned that, I was like, well, what's the point of that? I mean, if you already have something that's two-dimensional, why is it interesting to convert it to something two-dimensional? Well, of course, the answer is that it's not just that you change the dimensions of the thing. That's not what makes a linear transformation interesting. That's sort of a side effect that sometimes happens if you have a non-square matrix. But the thing that makes a linear transformation interesting is because it's computing something, right? If I know your annual salary and I need to compute your weekly salary so I know how much to pay you, let's say you're an employee of mine, right? Then I can compute that. I can take $52,000 a year, let's say that's your annual salary, just to make the math easy, and I can compute that that would be a $1,000 a week, that I have to pay you, right? That's a useful operation, even though we went from one dimension to one dimension, right? 52,000 is a one-dimensional number, and 1,000 is a one-dimensional number. So it's not like it becomes uninteresting simply because we're going from one dimension to one dimension. In fact, almost all of the mathematical operations you've ever done in your life, compute my gas mileage based on how many miles I've driven and stuff, every calculation practically goes from one-dimensional to one-dimensional. We're going to be looking at multidimensional to multidimensional, and it's certainly the case that it is an interesting operation, even if it goes from one size to the same size, right? Let's look at some examples just to make this concrete. And it's not like we're going to be dealing with these kinds of examples a lot, but just let me give you one. Let's say I've got a matrix here, and here's my matrix. This is going to be a 2 by 4. And I'm going to say 12, 1, 0, 0 on the top row, and 0, 0, 2.2 in the bottom row. Okay, now why am I doing this? This is an operation, and let's say we called this A. As we know just from looking at it, this is taking a 4-dimensional vector and turning it into a 2-dimensional vector. We are taking 4-dimensional inputs and producing 2-dimensional outputs. So I'm going to give you an example. Input, 6, 2, 93.2, 13. Now, in case you're wondering what the method of my madness is, here it is. This vector here, we're going to say the first element is my height in an even number of feet. The next one is a person's height in extra inches. So I'm 6'2", so that's why I have 6'2" as my first two entries here. This one here is going to be the person's weight in kilograms. And then what we're going to get is their shoe size. So suppose I had a vector that was a little representation of a person and some of their physical characteristics, and it was according to this format. What is the function of A? What is the purpose of multiplying this thing by A? Well, the answer is you're going to get out a 2-dimensional answer. And in this case, I've done the math. You can do it too to verify that I'm right, but you're going to get back 74,205. That's what happens when you multiply this dot producted with this. That gives you 74. And when you take this dot producted with this, that gives you 205. And I'm going to tell you that that right there is my height in total inches. And then this is my weight in pounds. So you give me any person as a sequence of 4 numbers, which is their height in feet and inches, their weight in kilograms, their shoe size here, and I will use my nifty A function to tell you what their height in total inches and their weight in pounds are, right? And you can see how this works. Basically what I've done is said, well, the first two are the only thing that matter for height. And that's why I have a 0 here and a 0 here, right? Because when I'm figuring out this first entry, I'm not going to do anything with the kilograms of weight. I'm not going to do anything with the shoe size. All I'm going to do is take the number of feet they are multiplied by 12 and add the number of extra inches they are multiplied by 1, and that's going to give me the total inches. And similarly down here, I actually don't care how many feet or how many inches tall they are or what their shoe size is if all I'm doing is computing your weight. That's why the only non-zero entry in the bottom is 2.2, because if I multiply 2.2 times somebody's weight in kilograms, I get their weight in pounds. Fun fact. Okay? So that's an example of a linear transformation, which might be useful. It might be that we want to find that out sometime, right? Notice, by the way, that we can't do something like BMI. If you know what BMI is, it's your body mass index, and it turns out to be this funky formula, which is like your weight times 700 something divided by your height squared or something like that, right? That is indeed a function. If you gave me somebody's weight and you gave me their height in feet and inches, I could tell you what their BMI is. That is a function. However, it is not a linear function. And if you think about how matrix vector multiplication works, there is no way to take height in feet, height in extra inches, and weight in pounds or anything else and compute the BMI with a matrix multiplication. And that's because in order to do so, you have to do more than multiply each entry times a constant and add them together. That's all you can do with a linear operation. That's all you can do with matrix vector multiplication, is take a number of elements, multiply each of them by something, and then add them all together. But you can't take 2 of the elements and multiply them together. You can't take 2 of the elements and square one and then divide one by the other. Those things don't fit in the linear model, and therefore you're not able to do something like BMI with matrix vector multiplication. Sounds limiting, and it is, but the thing is there's many places where the linear thing does apply, and it turns out that it allows us to do so many powerful concatenated operations that it turns out to be useful in its own right. Okay, let's do another example. Suppose I have, this is going to be really weird. Let's say I have a matrix here. Check this out. My matrix is going to be 6 by 3. I'm going to have 0, 1, 0 in the top row. I'm going to have 0.690 in the next row. Then I'm going to have 111.10. I'm going to have 0.880. I always close my zeros at the top. I got to work on that. 6.480 and 17.370. Now, what on earth could this possibly compute that's interesting? Okay, here's what. Let's say this is A. And let's say I've got three-dimensional vectors, which of course you knew I was going to say that, right? Because this is 3 wide. Therefore, we know right away that the input is going to be 3 high. And let's say this is something like 1979, 39.75, and 1 million. Okay, now what's the method to the madness here? Here's what. I'm going to say that this whole vector here represents a company that is trading on the stock market. And the first element there is the year the company was founded. And the second element here is their current stock price, what it's trading at on the New York Stock Exchange or whatever. And down here is the volume. That's the total number of outstanding shares. And what I do when I do this matrix vector multiplication is I'm going to get an answer that's going to be, of course, 6-dimensional because it is 6 tall. And what I'm going to get in this case is 39.75 and 27.3 and 4,395 and 34.8 and 256.6 and 687.8. What in the world is that nonsense? Well, here's what it is. This is how much it would cost you to buy a share of that company in dollars. And this is how much it would cost to buy a share of that company in British pounds, pound sterling. And this is how much it would cost if you were going to pay yen. And this is how much if you had euros. And this is how much if you had renminbi or yuan, which they're called in China. And this here is what it would cost in pesos, right? So again, I have a whole column of zeros and a whole nother column of zeros. That's obviously because that has nothing to do with how much a share of the company would cost if you bought it. And that has nothing to do with how much a share of the company would cost if you bought it. All that matters for that is the middle number. And I've simply multiplied it by a bunch of things and zeroed out the things I don't care about. So you can imagine this being an interesting operation that takes numbers in R3 and converts them to numbers in R6 and tells us these interesting things here, right? Notice I could not do something like total value of company. Wouldn't it be cool if I had a matrix, which if you gave me this red vector here, I could compute the value of a company, which is the stock price times the volume, right? Because if each share is worth that much, then if I multiply by the total number of shares, I get the total value of the company. Can't do it though, and the reason you can't do it is because even though that's a function, it is not a linear function. And therefore, it's not something that's, that we can do, right? So, bottom line, linear transformation is simply another way of looking at a vector. Every vector can be used as a pre-multiplier or a left multiplier of a vector of the appropriate size. It will produce a vector of another size, and that allows us to compute any linear function of those elements.